Our final talk today is William Faris, and he will talk to us about coalgebras and combinatorial constructions.
Thank you. When I came here, I was a little bit alarmed because I couldn't figure out any way to put the number of colorings of a graph into my talk. But last night I found a way of inserting this. So I'm feeling much better about the whole situation now. So my talk is about coalgebras and combinatorial constructions. And what I really want to do is to just make a kind of a remark. And that's that the equilibrium lattice gas problem, which is something that's very fundamental in statistical physics, is similar to the combinatorial constructions in enumerative combinatorics that are standard. In fact, I would like to argue that on an elementary level, they are identical. And I would also like to argue that on an advanced level, they are identical, but I won't be able to do that today. But I think Fernandez's talk tomorrow will make some of that clear. So at any rate, I basically want to talk about these, about the equilibrium lattice gas and the combinatorial constructions, and that they're really the same thing. But I also was thinking about this object. It's just one thing, and trying to understand what makes it work. And last year we had a seminar on Hopf algebras at our university, and I started to realize that some of those ideas might be illuminating in this context. So I want to explain, maybe not Hopf algebras, but coalgebras for a few minutes at the beginning. And what's the point of coalgebras? The main point is that it's a framework for convolution. And so I want to remind you what convolution is. So here is convolution from the point of view of an analyst. If you take two, say, probability measures, mu and nu, and you want to define their convolution, then one way to do it is by this operation here. The integral of the convolution with a arbitrary, say, bounded continuous function is given by this double integral on the right. And that's equivalent to other definitions of convolution that you're no doubt familiar with. Now, there are two stages to that definition. The first stage is to replace a function of one variable by a function of two variables. And the second stage is to do the integration with respect to the product measure. And these two stages really are, in this context of coproducts, going from a function of one variable to a function of two variables is a coproduct type of operation. And then, of course, the measure you integrate with is a product measure. So the convolution is obtained by applying a coproduct and then applying a product. So at any rate, let's see if I can make that more systematic. So to be more systematic, I need to do some algebra. And I'm not very comfortable with algebra. I saw these formulas the first time when we did this seminar, and I was completely mystified.
Bill, I'm sorry, just to go back a second.
Yeah.
What you said is true if I understand a measure to be a functional on functions, right?
That's right. So basically, you're trying to think of these measures as belonging to a dual space.
Right.
And in particular, this convolution is something that takes place naturally in a dual space. And the usual representation of convolution in terms of functions somewhat obscures that fact. Quite correct. So at any rate, this is the definition of an algebra. And this guy here is the associative law. Now, when I first saw this associative law written this way, I thought that the world had gone mad. But it just says that if you group one way first and then multiply two things and then multiply the third thing, or if you group the other way, you get the same answer. So if you apply this, M stands for multiplication of a pair, and M tensor, the identity, means multiply the first two things and leave the third thing alone. So if you apply this to a triple ABC, you get the product of AB times C equal to the product of A times BC, which is saying that AB times C is A times BC, which is the associative law. So I finally understood that was just telling me that was the associative law. And then there's also an identity law, which the identity in this, from this point of view, you think of taking the scalars and shoving the scalars into the algebra. So in particular, you shove the number 1 into the identity of the algebra. Now, algebras don't have to have identities, so you can't always do this insertion process. But when you do, the algebra has an identity, and the identity law has this same kind of mysterious algebraic formulation. This says basically if you apply the identity on the left and then multiply, you get back to what you started with. So that's a fancy way of formulating what it means for you to have an algebra. Now, the only reason for doing this in this context is to talk about coalgebras. Coalgebras are where you do the process backwards. And the idea is that that you take things and you split them up in perhaps more than one way. So it's unmultiplying. And the identity for unmultiplying is just like the identity for multiplying, except that the order of the operations has been reversed. So let's again apply it to an example. Now we start with a single thing, and this notation is a kind of symbolic notation due to a fellow graduate student of mine named Moss Sweedler that says break it up into different parts. And then here's breaking it up into different parts. And now you do it again, and you've broken it up into parts one way, and you've broken it up into parts the other way, and you're required that that comes out the same.
All right, you first give a definition for algebra and then give a definition for coalgebra. How about from to give a definition of orthogonal algebra from a coalgebra?
I'm not sure I understood the question.
Just now you gave a definition from algebra to a coalgebra. How about get orthogonal algebra from a coalgebra?
Again, you'd reverse things again, I guess. I'm not. Can we maybe not spend a lot of time on this part, because I would like to get to the second part of the talk. It's been a long day. I'm going to try and finish on time. Okay? I encourage questions, but if I don't know how to answer them, I'm not going to try. So anyway, so the order of decomposition doesn't matter. And there's also a notion of a coidentity. Now, for an algebra, you took a scalar and you shoved it into the algebra. For the coidentity, you take something in the algebra and you shove it into the scalars. So again, it goes backwards. And this law is actually written, the left-hand side is written backwards from the law for an identity. And so basically it says that the coidentity undoes the effect of the decomposition. Now, this kind of story looks totally mysterious until you see an example. So I'm going to give you the simplest example, this is the baby example in the subject. There are many more complicated combinatorial examples, but this is the only one I'm going to really need, and it sort of corresponds to the simplest possible combinatorial problem, which is basically breaking up a set into subsets. So, oops, I forgot. One more piece of abstraction. What is a convolution? A convolution is gotten by first applying a coproduct, then applying the operation. So the convolution takes place in a dual, as Alan pointed out. You take an algebra and a coalgebra, and you look at maps, linear maps from the coalgebra to the algebra. And the definition of a convolution of two of these linear maps is you co-multiply, apply the two transformations separately to the parts, and then multiply the answer. So that ultimately is what convolution is. Convolution is a co-multiplication followed by a multiplication. Co-multiplication breaks things into parts. The multiplication brings them back together again. So, I mean, if you apply it in this symbolic sense, you get that the convolution of L and M on an element of the coalgebra is given by multiplying in the algebra, L applied to the first part and M applied to the second part. So you decompose, transform the parts, and then multiply. And then the identity for convolution is obtained by applying first the co-unit and then the unit. So the co-unit takes you from the coalgebra to the scalars, and then the unit takes you from the scalars to the algebra. So, and that's the convolution for convolution identity. So here's my example. This example is so elementary that you'll decide after you've seen this example, you've been doing coalgebras all your life. You can think of the tensor product as going from functions of one variable to going to functions of two variables. So if you take a polynomial, p of x, the coproduct is p of x plus y. It's a polynomial in two variables. Now notice if you apply that to x to the n, you get x plus y to the n, which is given by this familiar formula in terms of binomial coefficients. So in some sense, this is the simplest combinatorial coalgebra because it corresponds to breaking up a set into subsets. The coidentity is given by evaluation at 0. And so that's easy enough. Now let's look at the dual of this polynomial coalgebra. So we're forgetting that polynomials are algebra, form an algebra. We're just looking at polynomials as a coalgebra. And so we're going to map to the scalars, which is an algebra. And so the convolution of two linear transformations, say applied to a basis vector, is gotten by breaking things up using this binomial expansion.
Say this again. So the coalgebra C is the polynomials as you just
That's right. And the algebra is just the scalars.
Is just the scalar.
Yeah.
That's the choice that you're making.
That's the choice we're making here.
Because in general, you can use any
Algebra.
coalgebra and any algebra.
Correct. So in particular, often you have a bialgebra, and you look at transformations from the bialgebra to itself. But that's a whole big story. I mean, I don't want to go into that. I'm trying to keep the simplest examples, keeping this introductory. So then, given one of these linear transformations, so what does it do? It takes a power of x, like x to the k, and gives you a number. So you can form this exponential generating function, and then the convolution turns out to be identical to multiplication of exponential generating functions. So multiplication of exponential generating functions is a classic example of convolution. Now you can look at derivatives of an algebra. A derivative of an algebra is something that satisfies the product rule. So the product rule says that if you take the derivative of a product, then you get the sum of two things. Well, a coderivative has got to satisfy the coproduct rule. So the coderivative, the coproduct of a coderivative is the sum of two things. Notice the order has gotten reversed. Here you multiply and then apply the derivative. Here you apply the coderivative and then co-multiply. But it's formally the same thing except for everything has been switched in order. And so you get that kind of expression, which is a kind of coproduct rule. So for example, let's look in our simple example for what a coderivative might be. A coderivative is just multiplying by x. If you take polynomial and you multiply it by x and then you promote it to a polynomial in two variables, it breaks up in that simple-minded way. Now this is humor for combinatorialists, but that's one way of thinking of Pascal's triangle as a coproduct identity.
This will help us a lot when we teach undergraduates.
Well, when you get to partitions and trees and things like that, maybe it would. Now, then you can ask, if you have a coderivative on the coalgebra, what happens in the dual space? Well, then you get a derivative, and if you calculate what that is in this example, it's precisely the usual derivative that we know and love. So that's the story on coalgebras and algebras, and that took 12 minutes, which is right on schedule. Yeah. Oh, he's going to throw me off.
Yeah, I just ask you the last three films. That it seems your results are always close in the commutative case, not in the field of complex, not in the field such as matrix and other kinds of things. Even in the last result, you consider L and M and two linear transform, but in fact, this result just can only hold that in L and M can complicate, you can get the result. If not can complicate, you don't get the kind of result. That's another term.
Yeah, maybe. This whole story here is commutative. Or sorry, it's also co-commutative. in the case of this particular example. This particular example is co-commutative. Many important combinatorial examples are not co-commutative. So this is a little bit special, this example. Even this special example, though, is the subject of an entire book by Rota called The Umbral Calculus, which is a study of this particular coalgebra. Yes?
Yeah, I only wanted to make an observation about Hopf algebras, an observation about Hopf algebras. Me and Joanna Ellis Monaghan did some work about Hopf algebras of graphs, such that some non-combinatorial polynomials are maps of Hopf algebras, from a Hopf algebra of graph to a Hopf algebra of polynomials. And the antipode of the Hopf algebra helped us a lot to understand negative values, and that was for the Penrose polynomial and the transition polynomials. So if you are interested in that, maybe we can talk later.
Well, I'm not going to do anything with this beyond what I've just said. She just referred to the notion of Hopf algebra. A Hopf algebra is something which is both an algebra and a coalgebra, and the coproduct is an algebra morphism, and the product is a coalgebra morphism, and there is an extra kind of inversion process, and that's what she was referring to. And and that inversion process is a kind of vast generalization of inclusion-exclusion ideas. And so this kind of thing you're talking about is the deep part of Hopf algebras, but I'm only just giving this as an introduction. It's not really my purpose. I just wanted to explain the language. Okay? So you're quite correct that there's much, much more you can do with this.
But in fact, if you first beginning from algebra, but don't contain some identity, so you have to construct some coalgebra.
Okay. At any rate, I don't care about coalgebras and algebras anymore. I want to talk about equilibrium statistical mechanics of particle systems and about combinatorial constructions. And I want to argue that these, sort of under the hood, there are these ideas that we've just been talking about. So first of all, let me give you a really quick introduction to one topic in equilibrium statistical mechanics. That's the lattice gas. So I'm going to assume that there are particles that I'm going to put into locations. So the crucial notion is that I have a set of n particles, so that's un, and I'm going to put that into a bunch of potential locations. Now, in the combinatorial language, the set of n particles is called the set of labels, and the locations are called colors. So that's part of my argument that the combinatorics and the statistical mechanics are the same. Now, in statistical mechanics, you want to calculate probabilities, and the probability of a particular particle configuration is given by a factor for each place where you try to put a particle in a location. So that's putting particles in the location. Those are called activity parameters. And then these 1 plus t things are interaction parameters. You put one particle in one location, another particle in another location, and there's an interaction that depends only on the locations.
You're allowed to put two particles on the same location?
Yes. It's an option, but a useful one. And then there's this normalization constant called the grand partition function, which makes the total probabilities add up to 1. So what do you want to compute? Well, we know from that you want quantities that are somehow stable when you look at very large systems. So if you go back and look at this system, if this set of locations is very large, each of these probabilities is going to be an extraordinarily tiny number. It's the probability of an exact configuration of particles, putting the first particle exactly in this position, the second particle exactly in that position, and so forth. And if there are many positions to choose from, each of these probabilities is going to be extraordinarily tiny. So you want to do something like the expected number of particles at a given position, and that's given by summing over the potential number of particles and then the possible particle configurations of the number of particles at that particular location times the probability of a particle being there. And then in the miracle of statistical mechanics, you rewrite that in terms of expressions involving partial derivatives of the partition function with respect to the activities. So these are standard statistical mechanical formulas. The expected number of particles is equal to this partial derivative expression times this variable of the log of the grand partition function as a function of the activities. Standard statistical mechanical formula. And then a very common device is to use the distributive law. Here you have this 1 plus something. I wrote it in that form because I want to use the distributive law. When you distribute this out, you get a big sum of terms, and these sums are indexed by edges of the graph on the set of particles. And so the partition function can be written as the sum over 1 over n factorial times particle configurations times this thing here, which is the sum of contributions, one from each graph on the set of particles. And then there's this product of activities. And then the great miracle of the whole subject, of course, is that the logarithm of the partition function, which is what we needed for that previous calculation, is gotten by summing over connected graphs. And I'll comment on that a little bit more later, but I think most people here are familiar with that story, so I'll postpone further comment for the moment. So here is where I can bring in colorings. I'm really happy about this. Take the example where the set of locations is the vertex set of a graph with loops, and where the interaction is -1 if this factor is -1 if you're in an edge and 0 otherwise. In that case, this partition function sum reduces to a sum over graph homomorphisms from the particle graph to the location graph. And if you take the location graph to be a complete graph on k vertices, then the graph homomorphisms are precisely the proper colorings of the graph with k colors. So I got something chromatic into the talk. Now, let me come to the last part of my talk. How am I doing on time? I'm okay? Are you keeping track?
Yes, you've got another 10 minutes.
Another 10 minutes. Okay, I'll try to finish in 5 minutes, and then we can have a free-for-all about whatever we want, maybe, or go have tea or something. So there's a fascinating book which is actually sitting on the table in the library out there by Bergeron, Labelle, and Leroux called Combinatorial Species and Tree-like Structures, published by Cambridge University Press some time ago. And it's a kind of attempt to systematize enumerative combinatorics. Now, it only partially succeeds because it does a really good job in what's called labeled combinatorics. Labeled combinatorics is when you're classifying actual objects rather than isomorphism classes of objects. And so the labels in that combinatorial language correspond to the particles in the physics language that I was using. Now, they also have some discussion of unlabeled enumeration, but they have to work harder. So I wanted to sort of look at these constructions, which are the common constructions of this area of statistical mechanics and of enumerative combinatorics, and try to look for coalgebra ideas under the hood. I mean, why does this whole business work? Why do exponential generating functions give us so much marvelous hold on so many things? So I want to ask something, what's the analog of a coproduct for one of these particle configurations? Well, what you do is you simply break the set of particles. So U is the set of particles. So U is the set of particles, P is the set of locations. This is the particle configuration in such a function. You break the set of particles into two disjoint parts in order. So you're basically picking a subset and a complementary subset. And that's a decomposition which is in some vague sense, at least resembles a coproduct.
It's also called a shuffle product, what you say.
Yeah. And now you can also try to find something that's analogous to a coderivative. This thing is obviously associative because you can break it up in either order if you break up things into 3 parts in order. Now there's a combinatorial coderivative, which is simply adding. So let's say you have one of these particle configurations. So for each particle you have a location, and there's a partial coderivative which corresponding to location P, which simply adds an extra external particle at location P. Or in the language of combinatorics, it adds an extra point, adds an extra label, and gives this label color P. So it assigns the location P to the extra particle. And so that obeys a coproduct rule, because if you decompose this set of particles together with the extra particle into 2 disjoint sets, then the extra particle can have been either in the first set or in the second set. So you get 2 disjoint possibilities. You either added it to the first set in the decomposition before you added the extra particle, or you add it to the second set. So it's precisely the coproduct rule that we saw in a purely combinatorial context. Now, I didn't find this in, well, no, let me not say anything about this. This is this is standard in both statistical mechanics and combinatorics in some sense. You can ask if there's something like a co-exponential. We have, exponential of a sum is the product of the exponentials. So the sum of a co-exponential should be the co-exponential of the coproduct. Everything goes backwards. So let's see how that works. So what is the co-exponential? You basically take your set of particles U and you partition it into as many parts as you want, not keeping track of order.
Non-empty parts.
Non-empty parts, right. And so it's a disjoint union of non-empty sets with no order taken into account. No order taken into account corresponds to the n factorial and an exponential. And then you can ask, what's this co-exponential rule that the sum, or kind of distributed sum of a co-exponential is the co-exponential of the coproduct? Well, the coproduct is taking the original set U and breaking it up into 2 subsets in order, V and W. And then taking the co-exponential of the product is partitioning V and partitioning W. On the other hand, you can do it the other, so that's the right-hand side here. Notice that in each part we had to do a partitioning. On the left-hand side, you first do the co-exponential. So you first partition like you did here, and then you split the sets in the partition into 2 parts, so that you're going to eventually apply one construction to one collection of sets and the other construction to the other collection of sets. And it's clear that these are totally equivalent operations. They're not only, have the same number of ways of doing it, but it's trivial. It's a trivial, matching that you do, a trivial combinatorial matching. And it's so trivial, I thought, gee, I'm embarrassed to talk about this. But then I wrote out the counting formula that you get from it, which is a formula about Stirling numbers of the second kind, and I started to have a little bit more respect for it. So that's what happens if you count according to the method on the left, and the other right-hand side is counting the partitions. Bk is the number of partitions. S and M is the number of partitions into m parts. Now, whoops, I have to go fast. So there's this concept of weighted sets, which are like sets, but instead of counting them, you attach weights to them. So you like an example we keep in mind is all these connected graphs. For each connected graph, we had a number. Let's skip over that. A combinatorial construction assigns to each particle configuration a weighted set, or to each colored set a weighted set. And so I just mentioned this connected graph construction as an example of such a construction. Now convolution. Convolution is gotten by coproduct, applying the two constructions separately. So the coproduct was breaking up things into their parts, applying the two constructions separately, two combinatorial constructions separately. And then the product is the product of weighted sets, defined appropriately. And combinatorial derivative is the dual of the combinatorial coderivative. And so you can start doing calculus with these things. For example, here we take the connected graph construction, take its partial derivative with respect to p. That's this thing that you get by adding extra particles. Then you do an operation which picks out a decomposition into just one element subsets and everything else. And when you finally go through this, you get the expression that we had for that came into the expected number of particles, the physically observable quantity. And the combinatorial exponential, again, it's first you take the co-exponential, that's this decomposition into this partition, looking at all partitions. Then you apply the construction to each part, and then you take the Cartesian product, which is the sort of the analog of the algebra product. And so, for example, if you apply that to the connected graph construction, you get the graph construction. And you can define an exponential generating function where this is the total weight of all the weighted set, and it has the property that the convolution of the combinatorial constructions goes into the product of the exponential weighting functions, exponential generating functions. The derivative law is satisfied just the way you would hope it would be. And the exponential property is just the way you would hope it would be. The exponential of the construction goes into the actual ordinary exponential of the exponential generating functions, as is well known in physics. And so in the end, you can get the expression that I wrote before for the expected number of particles at a point in terms of doing these graph constructions with this machine, with this combinatorial machine that you find in this book by these Montreal people. So the conclusion is that the statistical mechanical formulas are the combinatorial formulas, and that if you look under the hood, they have to do with this coalgebra ideas. Thank you.
Questions?
So you are saying maybe one of the conclusions is that many times exponential generating functions really give the results because they come as convolutions.
So the exponential generating functions really arise in terms of convolution applied to these combinatorial constructions. That's right. And when they don't work, it's because the corresponding algebraic structure is not there. And in fact, one of the things that we're going to learn tomorrow is, I guess, how to patch things up when they don't work. Thank you.